The research proposes an end-to-end approach for reconstructing the electrostatic potential volume of a sample directly from 4D STEM datasets. This method combines phase contrast imaging with atomic resolution electron tomography, overcoming limitations of traditional imaging methods. The approach uses multi-slice ptychography to compensate for the missing wedge effect and recover several slices at each tomography tilt angle. The algorithm is initially tested in simulation and experimentally demonstrated, recovering a nanoparticle with Sub-Ångstrom resolution. The reconstruction workflow consists of 3 steps: fast reconstruction using bright field data, estimation of global tomographic alignment parameters, and final reconstruction of the sample's 3D volume. This innovative method offers a significant improvement in imaging capabilities, particularly for thicker samples and light elements, with potential applications in materials science and structural biology. The end-to-end reconstruction workflow for 4D STEM data, as depicted in Figure 1, begins with the bright field reconstruction and aberration calibration. The weak phase images are reconstructed using the SSB method on uncalibrated datasets, and the optimal defocus for the bright field reconstruction is used for probe initialization. The multi-slice ptychography reconstruction then produces several slice images for each tilt angle, which are summed into 2D phase projections for joint reconstruction and alignment. To model partial coherence, a set of partially coherent modes is introduced, and the measured intensity becomes the incoherent sum of these modes. The multi-slice Tycho (MSP) algorithm is used for joint object, mixed-state probe, and position retrieval using multi-slice ptychography. This algorithm iterates through steps that include initializing aberration surface, calculating mean intensity, and setting up the initial probe and position refinement parameters. The algorithm then iterates through a loop that updates the volume, probe, and position parameters, outputting the final reconstructed volume, position, and probe. In the context of joint rigid alignment and linear tomography, the electrostatic potential of the sample is reconstructed, and a 2D projection of the sample can be formed by summing up the real part of all reconstructed slices. Using the potential projection for each angle, the affine transformation can be calculated using tomography, with the workflow shown in Figure 1b. The algorithm starts with loading the 2D projections and specifying the tilt angles. The 2D projections are preprocessed by applying an intensity threshold and downsampling the images. These preprocessed images are considered as the sinogram target of the loss function. The affine alignment includes 3D rotation angles and 2D spatial translation. The rotation matrix R is defined following the tomography convention in the popular cryo-EM processing package RelyOn. The iterative tomography alignment process consists of 2 nested loops. The outer loop updates the alignment parameters, which are then kept fixed in the inner loop. The inner loop performs the tomography reconstruction using an adjoint radon transform R on a 3D model of the particle, with the 2D projection images and the alignment parameters from the outer loop. A new set of projection images at the same tilt angles of the 3D model of the particle is considered as the sinogram model. The research paper presents a novel method for end-to-end ptychographic tomography, which integrates the reconstruction of the electrostatic potential volume, alignment parameters, and multimodal probes in a single computational framework. This approach is based on a forward model that utilizes the sinogram model and sinogram target, with the mean squared error loss function calculated using the amplitude of the modeled diffraction patterns and the measured 4D STEM data. The gradients of the amplitude loss with respect to the volume, wave function, and alignment parameters are propagated back to the computational graph using the AutoGrad framework of the PyTorch package. The end-to-end reconstruction process starts with initializing the volume, alignment parameters, and multimodal probes. It then iterates through each tilt angle, updating the volume and alignment parameters until convergence. The algorithm is formalized in Algorithm 3, where the input includes measured intensities, scan positions, Euler angles, global translations, initial probe modes, step sizes, binning, and iteration number. The simulation benchmark demonstrates the algorithm's performance on a cube-shaped PT at aluminium oxide core shell nanoparticle. The electrostatic potential volume of the sample was built using Prismatic 2.0 simulation code, and 10 frozen Phonon 4D-STEM datasets were collected and averaged. The MSP reconstruction produces a 10-slice volume, which is then summed up to a 2D phase projection for each tilt angle. These projections are fed into the joint linear Tomo algorithm, yielding an initial volume 5 and the global alignment parameters theta*operator and tau*operator. The reconstructed alignment and the alignment ground truth were plotted in Fig. 2a, showing acceptable alignment differences within 0.4a for half of the reconstructed alignment, with the maximum difference being 0.8a. The volume result from the joint reconstruction showed high accuracy compared to the ground truth, as demonstrated by the slice images at the same depth, both with a thickness of 1a, in Fig. 2bc. Both high Z atoms, platinum, and low Z atoms, oxygen, were recovered and present in the slice images. Some shadow, or faded atoms, appeared in the middle area of the reconstructed slice image, mainly due to the crosstalk between slices. The research paper discusses the development of a novel end-to-end reconstruction algorithm for ptychographic tomography, focusing on the experimental demonstration and resolution analysis. The algorithm utilizes a multi-slice ptychography and alignment procedure, followed by a joint reconstruction process. The experiment involves collecting a 4D-STEM dataset at various tilt angles, with a dose reduction test to demonstrate the efficiency of the algorithm under low-dose conditions. The results show a significant improvement in resolution, achieving a resolution of 3.28A with a total fluence reduction of 12 times compared to previous methods. The study also highlights the potential for further resolution improvement by increasing the efficiency of the implementation. The paper concludes by emphasizing the potential of this algorithm for imaging beam-sensitive materials. Here is a combined summary of pages 9 and 10. The authors present an end-to-end joint reconstruction algorithm for multi-slice ptychographic tomography, which provides a new method for compensating for the missing wedge effect in electron tomography. This limitation arises from the restricted tilt range due to the strong electron-matter interaction and sample thickness limitations. The algorithm expands the 2D projection to a 3D volume at each tilt angle, recovering additional information in the missing wedge direction, as indicated by the Bragg peaks in Fourier space. In real space, the reconstructed atoms in the beam sectioning direction exhibit minimal elongation and streaking effects, even with 90 degrees of missing wedge. The authors demonstrate the algorithm's potential under low-dose conditions, achieving a near-isotropic 3D resolution with a tilt range of plus or minus 45 degrees in simulation and plus or minus 53 degrees in experiment, with relatively low electron doses. They also show the ability to image both high and low atoms in the same volume with a tilt range of only 90 degrees. The experimental demonstration involves a Te nanoparticle and a carbon nanotube, with a tomographic tilt series acquired using the TEAM 0.5 microscope and TEAM stage at the National Center for Electron Microscopy in the Molecular Foundry. The 4D-STEM datasets were recorded with full diffraction patterns over 800 × 800 probe positions at each tilt angle, with an accumulated fluence of 1.79 × 10 to the power of 4 A squared per projection and 6.28 × 10 to the power of 5 A squared for the entire tilt series. The raw data is available on Zenodo, and the code will be published open source on GitHub and Zenodo upon publication. Future work involves sub-pixel position refinement in the end-to-end reconstruction, atom tracing or atomic model building using the reconstructed volume, and exploring application-tailored experimental configurations. The research paper discusses advanced techniques in electron microscopy, focusing on ptychographic tomography and its applications. It highlights the importance of accurate phase retrieval for high-resolution imaging. The authors present various methods for phase retrieval, including iterative algorithms and the use of phase plates. They also discuss the significance of minimizing the missing wedge in tomography and the benefits of dual-axis tomography. The paper concludes with the presentation of a new method for reducing the missing wedge using dual-axis tomography. Throughout the paper, the authors emphasize the importance of precise control over the microscope's parameters and the detector's settings for achieving high-quality images. The experimental parameters for end-to-end ptychographic tomography, as outlined in Table 2, detail the settings and conditions used in the study. The microscope voltage was set at 80 keV with an electron gun type of SFEG, featuring a source size, FWHM, of 0.8 A. The CC value is 0.6 mm, with a defocus spread, FWHM, of 6 nanometers and a convergence semiangle of 25 mrad. This setup provided a depth of field of 9 nanometers. The detector used was a 4D camera operating at 87 kHz, with a detector pixel size of 4.14 × 10 to the 3 A/1, which was binned to 0.0272 A/1. The detector outer angle was 50 mrad, and the reconstruction pixel size was 0.397 A. No energy filter was employed, and the experiment involved 36 projections, out of which 26 were used in the analysis. The tilt range spanned from 53.9 to 52 degrees. A total of 34,560,000 diffraction patterns were recorded, with 8,423,259 manually selected for further processing. The stem step size was 0.397 A, and the dwell time was 11.49 microseconds. The probe current measured on the flue screen was 40 picoamperes, resulting in an electron fluence accumulated in the experiment of 6.28 × 10 to the 5 E/A². For the reconstruction, an electron fluence of 4.4 × 10 to the 5 E/A² was utilized, with each projection receiving an electron fluence of 1.72 × 10 to the 4 E/A². On average, 2,726 electrons were present in each diffraction pattern, and 1,700 electrons were detected per diffraction pattern, yielding a detection efficiency of 62.3%.